Welcome to Mythosium, the channel where we explore the ideas that push the limits of human understanding and reveal the hidden structures shaping the world. Today we're diving into a topic that stands at the frontier of physics, mathematics, and computer science. It's a subject surrounded by excitement, confusion, and mystery. Many people have heard that quantum computers are revolutionary, but the reasons behind their extraordinary potential are often misunderstood. Quantum computers are not just faster versions of the devices used today. They are fundamentally different machines, built on principles that challenge everyday intuition. To understand what makes them powerful, it's necessary to rethink what computation actually is. Traditional computers are built from bits, the smallest units of information. A bit can be either 0 or 1, and digital computation progresses by manipulating these values through logic operations. This system has enabled extraordinary progress. Modern processors contain billions of transistors, each switching billions of times per second. But as powerful as classical computing has become, it remains bound by the rules of classical physics. Each operation handles a specific configuration of bits, and each step corresponds to a definite state. Quantum computing takes a radically different approach. Instead of bits, it uses qubits, quantum mechanical objects that can exist in superpositions of 0 and 1 at the same time. A qubit is not merely a probabilistic mixture of 0 and 1. Instead, it occupies a combination of states described by amplitudes, which encode both magnitude and phase. The superposition property is not just a trick, it is the foundation of quantum computation, because it allows a quantum system to represent many states simultaneously. As the number of qubits grows, the number of possible states grows exponentially. A classical bit string with 50 bits can represent one specific number out of roughly a quadrillion possibilities at any moment. But a quantum state of 50 qubits represents a superposition of all those quadrillion possibilities at once. The system is not exploring each state one at a time. It is representing all of them simultaneously in its wave function. This massive increase in representational capacity is one of the reasons quantum computers might unlock new computational power. But superposition alone does not provide that power. A machine that simply stored many states would not automatically produce useful results. The key lies in how quantum algorithms manipulate amplitudes. Quantum operations rotate, interfere, and entangle qubits in carefully controlled ways that amplify desired outcomes and cancel undesired ones. Through this interference, quantum computers guide computation toward correct answers while suppressing incorrect ones. This mechanism allows them to solve certain problems dramatically faster than classical computers. Entanglement is another core ingredient. When qubits become entangled, their states can no longer be described independently. A measurement on one qubit instantaneously determines the state of another, even if they are physically separated. Entanglement isn't just a curiosity. It is a computational resource. It allows quantum systems to correlate information across many qubits in ways classical systems cannot mimic without exponential cost. Many of the most powerful quantum algorithms rely on entanglement to link together vast spaces of possibilities. Interference is equally essential. Quantum states can combine constructively or destructively, similar to how waves overlap. A well-designed quantum algorithm uses interference to increase the probability of correct outcomes and decrease the likelihood of incorrect ones. This is why quantum computers can sometimes solve specific problems with far fewer steps than classical machines. They exploit the natural wave-like behavior of quantum systems to scope the probability landscape of solutions. One of the earliest and most famous examples of quantum advantage came from an unexpected source: encryption. Much of modern digital security relies on a problem known as factoring, breaking a large number into its prime components. The structure of this problem makes it incredibly difficult for classical computers when the numbers involved have hundreds or thousands of digits. The difficulty of factoring large numbers is what protects secure communication digital signatures and many global financial systems. For decades, this security rested on the assumption that no efficient algorithm existed to solve the problem. Then a breakthrough occurred. Shor developed a quantum algorithm capable of factoring large numbers exponentially faster than classical algorithms. Instead of trying each factor or examining patterns in the number one at a time, the algorithm uses quantum interference to identify periodicities in a mathematical function related to the number. This approach transforms factoring from an intractable classical problem into one solvable by a sufficiently large quantum computer. Although today's quantum computers cannot yet run the algorithm at full scale, the discovery changed the understanding of computational limits. Another influential quantum algorithm came from work by Love Grover, His approach addresses the problem of searching an unsorted database. Classically, searching requires checking entries one by one, but quantum mechanics allows the process to be accelerated. Through amplitude amplification, a quantum search algorithm increases the weight of the correct answer in the wave function, making it more likely to be observed. While the speedup is not exponential, it is significant and broadly applicable. This demonstrated that quantum computers can enhance a wide range of search and optimization problems. These early algorithms showed that quantum computation is not merely a theoretical curiosity. It offers concrete advantages rooted in physical principles, not computational tricks. But understanding why quantum computers are powerful requires examining the nature of information itself. Classical information is discrete. Bits flip, memory stores ones and zeros, computation proceeds step by step. Quantum information is continuous in amplitude space and behaves according to linear algebra over complex vectors. This shift from discrete logic to continuous wave function evolution is profound. It enables a completely different style of computation, one that is uniquely suited for problems with deep mathematical structure. Quantum computers excel at problems that involve patterns in large spaces, periodicity, or complex transformations. They are especially suited for simulating quantum systems. Classical computers struggle to model molecules, chemical reactions, and many-body physics because the number of quantum states grows exponentially. Quantum computers, however, represent these states naturally. They don't emulate quantum mechanics. They operate according to it. This makes them promising tools for advancing chemistry, material science, and the development of new energy technologies. For example, simulating the behavior of electrons in a molecule is a challenge that scales beyond classical capabilities quickly. Quantum computers can potentially handle such systems with far fewer resources. The potential impact extends into optimization. Many real-world problems, from logistics to finance to machine learning, involve exploring large landscapes of possibilities. Quantum computers offer new methods for sampling these landscapes, escaping local minima, and guiding systems toward optimal solutions. While these techniques are still in development, they reflect the versatility of quantum computation as a platform for exploring complex problem spaces. To understand why quantum computers have not yet taken over the world, it's important to examine their limitations. Quantum states are fragile. They interact with their environment easily, losing coherence and becoming classical. This problem, known as decoherence, disrupts quantum computation. Qubits must be isolated, stable, and precisely controlled. Any environmental disturbance, heat, vibration, electromagnetic noise, can collapse a superposition. Building machines that maintain coherence long enough to perform complex computations is extremely difficult. Error correction is another challenge. Classical computers can handle errors through simple redundancy. Quantum error correction is far more complicated because qubits cannot be duplicated directly. The no-cloning theorem prevents copying quantum information. Instead, quantum error correction encodes logical qubits into entangled states of many physical qubits. This requires a large overhead. A fault-tolerant quantum computer capable of running large-scale algorithms may need thousands or millions of physical qubits for just a few hundred logical qubits. Despite these challenges, progress is steady. Experimental systems have grown from a handful of qubits to devices with dozens or even hundreds. Different physical implementations, superconducting circuits, trapped ions, photonic qubits, topological qubits, offer unique strengths. Researchers continually refine techniques to improve coherence, collectivity, and gate fidelity. While a fully practical large-scale quantum computer remains under development, the pace of advancement is increasing. Understanding the power of quantum computers also requires appreciating how they complement classical computers. Quantum devices are not replacements for traditional processors. Instead, they are specialized tools. Classical computers remain far superior for general-purpose computation, logic-heavy tasks, and operations requiring high precision. Quantum computers shine in areas where classical algorithms hit combinatorial explosions or where nature's underlying quantum structure becomes impossible to simulate digitally. The future will likely involve hybrid systems where quantum and classical machines collaborate. Classical processors handle control, error correction, and pre-processing. Quantum processors tackle the specific sub-problems where they offer true advantage. This hybrid vision reflects a deeper truth. Computation is not a monolithic concept. It is a spectrum defined by the physics of information. Classical physics gave rise to classical computing. Quantum mechanics gives rise to quantum computing. Each regime has strengths and limitations. The emergence of quantum computing demonstrates that the laws of physics define what is computationally possible. The universe sets the rules. Humans build machines that attempt to follow them. There is also a philosophical dimension. quantum computers force a reconsideration of what it means to compute. In classical computing, the system follows a definite sequence of steps. In quantum computing, the machine explores a high-dimensional space of possibilities simultaneously, guided by wave interference. The answer emerges not from checking each possibility individually, but from manipulating the entire landscape of amplitudes. This process is invisible to intuition because nothing in everyday experience behaves like it, yet the universe operates this way on the smallest scales. The power of quantum computers comes from leveraging the fabric of reality itself. Superposition expands representational capacity. Entanglement creates correlations impossible to achieve classically. Interference sculpts probability distributions toward meaningful outcomes. Together, these properties allow quantum computers to process information in ways fundamentally different from classical logic. They bypass the limitations of binary switching by embracing the full complexity of quantum mechanics. Looking ahead, the impact of quantum computing could be profound. In chemistry, new materials could be discovered through accurate simulation of molecular interactions. In medicine, drug design could accelerate through precise modeling of biochemical pathways. In logistics and optimization, complex global systems could be managed more effectively. In physics, quantum simulators could shed light on phenomena currently beyond reach. Much of this potential is still theoretical, but the trajectory of research suggests that quantum computing will eventually transform many fields. Even if large-scale quantum computers remain years away, understanding what makes them powerful deepens appreciation for the connection between computation and physics. The digital world is built on classical approximations. Quantum computing reminds us that beneath those approximations lies a richer structure. By building machines that operate according to quantum rules, humanity is not merely advancing technology. It is aligning computation more closely with the reality it seeks to describe. At Mythosium, we explore these ideas because they reveal how scientific progress often comes from questioning assumptions, reimagining what is possible, and embracing the unfamiliar. Quantum computing challenges intuition, but it also expands imagination. It shows that the universe contains computational possibilities far beyond anything classical systems can access. And as the field advances, the boundary between what is possible and what is practical will continue to shift. If this kind of exploration inspires curiosity, if the intersection of physics, mathematics, and technology sparks imagination, make sure to subscribe. There are many more frontiers to uncover, many more mysteries to explore, and many more ideas waiting to reshape understanding of the world. Thanks for watching, and stay curious.